Okay, let's do another example where we make use of the TDS equations. This one will involve TDS equations for an ideal gas. This problem statement is in the Lecture 25 notes. And as with the previous example, I'm going to go ahead and just go step by step through the solutions for you. So in this problem, we have nitrogen entering an insulated compressor, and it's operating at steady state at a given pressure and temperature and a given mass flow rate. And then we're also told the exit pressure. We're told we can neglect kinetic and potential energy through the compressor, and that we can model the nitrogen as an ideal gas with a specific heat ratio. Remember that the specific heat ratio is our K value here, so K is 1.391. It's very close to that for air because air is primarily made of nitrogen. And we're also told the specific heat at constant pressure. So this is the CP value here as well. So we're given those. And so because those are given, we can assume that we're dealing with constant specific heat. So it's really a perfect gas since we're given just a single value for the specific heat. We're asked to determine the minimum theoretical power input required to operate the compressor and the corresponding exit temperature for this case. So this is similar to the other example that we did where we're trying to find the minimum power. So this will involve the first law, since that's where you calculate the power from. And then we'll also make use of the entropy equation there as well, since we want to minimize since the entropy equation involves entropy production, and we want to look at the internally reversible case. And then the part B is to find the exit temperature, or no, if the exit temperature is 397 degrees C, determine the power input in the compressor efficiency. So we'll talk about compressor efficiency at the very end of this example. Okay, so we're trying to find the power to operate the compressor. So we'll apply the first law to a control volume surrounding the compressor. That's shown in the following figure. One thing that I did not do that I should have done is included our energy flow diagram. So we have some power going into our compressor. I'm just drawing it into because that's the same sign that I have in my first law here. So we write out our first law expression for that particular control volume. We're assuming that we're dealing with a steady flow, so the dt goes to 0. We have one inlet and one outlet, so the m dot 1 and the m dot 2 are just m dot from conservation of mass. We're neglecting changes in kinetic and potential energy, so those terms go away. So we're just left with m dot times h1 minus h2. We're assuming that the compressor is well insulated so that it's operating adiabatically, so the q dot term goes to 0. And so in the end, when you substitute back into the first law, we'll get that the power acting on the control volume is equal to the mass flow rate times the change in the specific enthalpy across the compressor. This part, hopefully you know how to do by now. I think everybody should be fine with that. We're going to further assume that the nitrogen behaves as a perfect gas. Again, we're given that the specific heat is just a single value, so that implies that we're assuming that the specific heat is a constant. And with that being the case, we know that for a perfect gas, the change in the specific enthalpy is just Cp times the change in temperature. And so that's what we've used to go from equation 5 to equation 6. Okay, so everything I think is pretty straightforward up until this point. I think everybody would know how to get to this point. Now the next thing that we want to do is we're specifically interested in finding the minimum power required to operate this compressor. So in order for it to be the minimum power, just like in the previous example, we want to consider an operation that is internally reversible, right? So no entropy production. So we want it to be internally reversible, and since the flow is adiabatic and reversible, that means it will also be isentropic. Remember that we talked about this in the actual lecture notes, that adiabatic plus internally reversible means that you'll have isentropic an isentropic process. This comes from the entropy equation, which I'm just jotting down here as a reminder. Sorry, it's so small. So there's the entropy equation. If it's adiabatic, the heat transfer term is 0. If it's internally reversible, then the entropy production is 0, and then what you're left with is the change in entropy is 0, which means it's isentropic. And we're interested in the internally reversible case because that will be that will give us the minimum power. So since again it's adiabatic and reversible, we're dealing with an isentropic case. So what we're dealing with now is the isentropic process involving a perfect gas. So we have a perfect gas isentropic process. If you go back to our notes that we used for lecture 25, you'll see that we can relate properties using the following ratios here. So this is equation 7 that the ratio of the final pressure to the initial pressure, so P2 over P1, will be the ratio of T2 over T1 raised to K over K minus 1. Again, the K here is the specific heat ratio. So these come from the perfect gas relations for isentropic processes. And you'll notice that I have an S here, like 2S. The S refers to the fact that I'm dealing with an isentropic process. The S is just a notational device so that you know that when I write this equation out, I'm specifically trying to solve for the temperature for this isentropic process. So we rearrange that equation to solve for the temperature. Since we know we're given the pressure ratio across the compressor and we're given the initial temperature, the inlet temperature, so we can solve for the temperature at the outlet for this isentropic process. So we're given the various values, we're given the temperature, the pressures, the specific heat ratio, so we can solve for the final temperature. And again, I'm going to use absolute temperatures because I'm dealing with, in the derivation of this, we use the ideal gas law. So you definitely need to use the absolute temperatures. Anytime you're dealing with ratios, you need to use absolute temperatures, absolute pressures. Okay, so this would be the temperature for the minimum work case or the reversible case. And then we can go ahead and substitute that temperature back into our equation for the work. This is equation 6. So now we know the outlet temperature. We can go ahead and plug in our values to find the minimum power. So it comes out to be 82.8 kilowatts for this particular case. Now, let me go, so that's part A. Determine the minimum theoretical power, we just did that, and the corresponding exit temperature, which we just did. Now for part B, we're told the exit temperature. Okay, so let's determine the power output if we're given that temperature of 397 degrees C. So this might be what you would have in practice. If you were operating this compressor, very likely you would be measuring the pressure and temperature at the inlet and the pressure and temperature at the outlet. So you would actually have the temperature at the outlet. So if you want to determine the power output, for that case, all we need to do is go back to equation 6 here and then plug in the actual temperature, T2. So we can do that. That was the 397 degrees Celsius or 670 Kelvin. And so you see that the actual power for this particular case is 106 kilowatts. So it takes more power to operate it for the actual temperature than the minimum reversible case, which was only 82.8 kilowatts. So then the very last part of the problem was asking to find the efficiency of the compressor. Now, we'll come to this topic in just a couple of lectures, but for now, you can think of the efficiency as the amount of power that you'd have to put into the compressor for the minimum case divided by the amount of power for the actual case. So that ratio will always be less than 1, right? So the minimum power you have to put in is always going to be the smallest value. It'll always be less than the actual value. So the efficiency would be less than 1. Hopefully, just think about the logic there. Hopefully it makes sense to you. You don't have to memorize an equation or anything. It's just the minimum power you have to put in divided by the actual power, and you know it'll always be less than 1. So we can just substitute in our minimum power here, our actual power there, and then you get an efficiency of 78%. I mentioned in the lecture notes that this is why we go through this entropy equation and talk about internally reversible and internally irreversible processes, is because when we start looking at the reversible cases, it sets the ideal case value for many of these problems. Like in this case, it was the best case scenario for the minimum amount of power we would have to put into this compressor. Right? So it gives us our target, what's the best case, and then we can always compare our real case to that target. So here we know that our compressor is really only operating at 78% efficiency. Perhaps we can do a little better, right? It gives us a way to determine how well we're operating. There's an upper limit. The best that we can do is 83 kilowatts. We're not quite there. We can do a little better. Okay, so it gives you an idea of where to invest your energy to try to redesign things. Now, the rest of this problem statement says, if we assume that we're dealing with an ideal gas rather than a perfect gas, then we can calculate the change in entropy a different way. Okay, so when we went back, let me go back here for a second. When we used these equation 7, that was for an isentropic process involving a perfect gas, one with a constant specific heat. So now what I want to do is consider an ideal gas where the specific heat can vary. So an isentropic process for an ideal gas. So this is, again, an isentropic process in an ideal gas where the CP varies with temperature. Okay, so for that case, if you go back to our lecture notes, the change in entropy for an ideal gas looked like this. We had those S0 values, if you recall those. And since we're dealing with an isentropic process, the change in entropy is equal to 0. So we can rearrange that equation. And so it looks like this. Notice that I've actually switched from S0 to an S0 with a bar over it, bars over all these things. The reason I did that is because if you look at the tables, the ideal gas tables, most of the different materials in there are given in terms of the units of like S0 bar will be kilojoules per kilomole Kelvin rather than kilojoules per kilogram Kelvin. The only one that is given in kilojoules per kilogram Kelvin is air. All of the other substances are given in terms of kilomoles. So since we're dealing with nitrogen, what I've done is I've switched over to all of the terms here having kilomoles rather than kilograms. And so the gas constant, so basically the way you do this is you multiply everything through by the molecular weight. I believe that's correct. Yeah, you multiply everything through by the molecular weight and it turns it all into kilojoules per kilomole Kelvin. Mm-hmm. Okay, so then you see that the gas constant becomes the universal gas constant over here. So again, the only reason I switched to that is because that's how the tables are arranged. So if you go to the tables, you can find the S bar naught value at the inlet temperature. And here I actually use the Moran and Shapiro tables at the back of your textbook, but you can use the Excel tables. You'll get a slightly different number, but it doesn't matter because we're dealing with differences in S0 values. P2 over P1, again, you want to use absolute temperatures here, so that's straightforward. The universal gas constant, straightforward. And then when you solve the equation, you'll get the value for S2 naught. Then you can go back to your table and then interpolate the corresponding temperature for that, which comes out to be 594 Kelvin. So if you use the tables, which are for an ideal gas where the CP can vary, you get a temperature of 594 Kelvin. And when we did a perfect gas assumption, it was 592 Kelvin. They're a little bit different, less than 1% difference. The one that's more accurate is the 594 Kelvin. It's more accurate because the CP is allowed to vary with temperature. the perfect gas assumption, the CP is a constant, which is an approximation. But either way, the difference in the values is very, very small. So both would, the perfect gas assumption is a very reasonable approximation here, just only minusculely less accurate. Okay, now I know I went through this one kind of quickly, and I don't believe you have a printout of this solution. I'm not going to provide it because I want you to go back and sort of work through this problem on your own. Of course, you can always look at the video and see all of the different steps that I've put together here, but I want you to do this one without actually having the printout available.